Okay, in this video we're going to be talking about equivalent impedance. Just like we had equivalent resistance, we have equivalent impedance. And this is going to be important for us for when we do power computations. So when we're going to be dealing with power, we're going to need to talk about equivalent impedance. Now, of course, we're not talking about power in this module, but that will be something we will cover in a later module. Now, the good news for this is that we find equivalent impedance the same way we found equivalent resistance. Because remember, when we're in phasors, everything obeys our Ohm's law. So that's actually very helpful for us. So the strategies here are, first, of course, to transform everything into phasors. And then compute equivalent impedance. Now, one thing we have to make sure to remember here when we compute equivalent impedance is that we really want to start from the opposite side of the terminals, typically where the impedance is being measured from. You don't want to start at where the impedance is being measured from. People make mistakes and they think things are in series when they're not, or they think things are in parallel when they're not as well. So let's look at a really basic example to start with, and then we'll look at something maybe a little bit more complex. So let's first look at (200 millifarads). This will be 2 henries. This is going to be 10 ohms. This will be 5 ohms. And I haven't necessarily picked these to be pretty numbers. I'm just picking them randomly, somewhat randomly. And then omega is equal to 5 radians per second. Because we need to know what frequency the circuit's operating at in order to compute the impedances, because we have to use our formulas to compute the impedances. All right, so let's go ahead and compute and do our first transform everything into phasors. So the 10 ohm just stays as 10 ohm. The 5 ohm stays as 5 ohm. Now let's look at the 200 millifarad capacitor. Well, doing impedance of a capacitor, knowing that it's minus J over omega C, we would get that this is minus J over 5 times 200 millifarads, which is actually equal to negative J ohms. So this is negative J ohms. And then let's do the 2 Henry inductor. We know that the impedance for an inductor is J omega L. And so that would be J times 5 times 2, J 10 ohms. So this is J 10 ohms. And then this one is another capacitor. So that would be minus J over 5 times 500 millifarads, which gets me negative J 0.4. Negative J 0.4. All right, so these are all my components here. Now, I have to combine these in order to find my equivalent impedance. Now, the equivalent impedance, we have these two terminals here. So I'm going to be looking in on these two terminals here. Now, I see a lot of people start on this left-hand side here and say, okay, well, I should just put these are like, oh, look, these are in series or something like that, and they add these three things together in series. That is not correct. It's not correct because, remember, in order for things to be in series, there can only be two connections to them, right? That's something to be in series. There can only be two things connected together and add a node. And if I look at this node here, you might say, well, yeah, it's just the resistor and the capacitor that are connected together. But there's also this wire. You might say, oh, you can ignore wires. You can't ignore wires when you're doing impedance here, because I'm going to have, for instance, I might have an ohm meter hooked up here, or I might have a network analyzer hooked up here, which means that that network analyzer is now connected to these things, and these are not in series anymore, because they're just not in series to begin with. And the same thing down here. These are not in series. So when I say to compute equivalent impedance, I say the general thumb is always start on the opposite side from where you're measuring. So I'm measuring on the left-hand side, so I'm going to start all the way over on the right-hand side. Okay, so then if I start all the way over on the right-hand side, I can see here, well, look, I've got this resistor and this capacitor in parallel. Now, because everything has been transformed into phasors, all of the things we learned about combining resistors in parallel and series still obeys. So we could do, for instance, there's two ways we could compute this impedance inside that box. I could say Z is equal to 1 over 5 plus 1 over minus J 0.4, all of that to the negative 1 power. Or remember, when you have two things in parallel, you can do where I multiply them. So I have 5 times negative J 0.4 divided by adding them. 5, and well, if I add, it would be 5 minus J 0.4. So this is what I'm going to do, and I'll need to pull up my actual complex number calculator here. Come on. Okay. So we have 5 times actually I need to do this. 5 times negative, actually let's do it like this, negative 0.4 I divided by 5 minus 0.4 I. So it does those steps for me. And it gives us this in fractional form, but then it also gives us this in decimal form, which is nice because we really want it in a decimal form here. It tries to go through and show all the steps. I don't necessarily care about the steps. I just want to know what the answer is. So we have 0.0318. So this is equal to 0.0318 minus j.397. Okay, and then I can go ahead and redraw my circuit a little bit. Whoa, that was weird. Well, I don't know if it just went there, but my computer just kind of went a little haywire there for a second. So I don't know what happened on the video, but I'm back here. So let's go ahead and say, let's redraw the circuit. So I have this as negative j, 10. And I'm just going to put a little box here. And this is j10. And then inside this box is 0.0318 minus j.397. And now all of these things, whoops, let's use a different color here. All of these components here are absolutely in series. And so I can add all of those up. And so if I add all those up, I'd have 10 plus 0.0318 minus j.397 plus j10, which would get me 10.0318, which I'll round that in a second here, plus j, and let me use a calculator to get that so I don't make a silly arithmetic mistake. 10 minus 0.397, 9.603 ohms. And now this is 10.0318. I mean, technically, should we keep all the decimal points? Yeah, maybe, I guess. But I'm going to shorten this just to 10.03 plus j 9.603. Because then we have the same number of significant digits. And now my circuit becomes minus j. And I have a little box here now. And inside that box is 10.03 plus j 9.603 ohms. And now that's in parallel with this minus j. And so I'll go ahead and do this time. No, I'll go ahead and do the multiplication. You can do it the other, well, no, I think I'll change my, I'm sorry, I keep getting, no, I'll go ahead and do it the other way here. So I'll do this as minus 1 over minus j plus 1 over 10.03 plus plus j 9.603 the whole thing to the negative 1. Now I could have still done what I did originally, which is the multiply and add, but let's go ahead and do it the other way as well. So I'm going to need to pull up my complex calculator here. So let's clear this expression out. So I'm going to have here, first off, I'm going to just have 1 divided by minus j, so minus I, plus 1 divided by, parenthesis, 10.03 plus 9.603 I got my caps on by accident. And that's all to the -1 power. And if I do that, it spits out an answer here. That this is equal to -0.057. No, sorry, not negative, 0.057 4 minus J 1.04, or actually 1.05 ohms. And so this is my equivalent impedance. Now you might say, man, that was a lot of work for a relatively easy example. And the only thing that's challenging about these, again, is the fact that we're having to use complex numbers. And so we have to be careful. Now we have our calculators to help us out with this, but that's why I like to kind of take it one step at a time. Now, one thing that is often something I ask on quizzes that's not necessarily asked in the homework is what components could be used to represent this. Well, I'll give you first thing here is that the real part of an impedance, this is always a resistance or a resistor. It's a resistance, but it's always a resistor because the resistor is the one that has the real. Remember, if you look at remember Z sub R is R, real value. But then Z sub L is J omega L, and Z sub C is minus J over omega C. And that can kind of tell you right away which this one would be. This one would be a capacitor. How do I know it's a capacitor? Well, think for a second. And if you think for a second, it's because of this negative right there. Because omega is never going to be negative. L and C are never negative. So the only way to have a negative J is the fact that you started with a capacitor. So this equivalent circuit could be represented. I mean, the original circuit is not that it has, just a capacitor and a resistor. The original circuit had capacitor, resistors, and an inductor in it. But the equivalent circuit could be represented as a single resistor with a capacitor, and this would be a 0.0574 ohm resistor, and this would be a minus J 1.05 ohm capacitor impedance. Okay? Well, I'm going to end this video here. We're actually a little long on this video anyway. Next video, I'll do another example using impedance.